Welcome. Today we begin 5.2, the definite integral, and today we will talk about limits of Riemann sums and net area. So, net area and the definite integral. The net area between the graph of a function and the x-axis and over the closed interval from a to b is denoted this way. We call this the definite integral from a to b of f of x dx. For example, let's take a look at the picture on the right. That shows the definite integral from 0 to 2 of 9x squared minus 16x plus 4. And geometrically, we think of it as the area above the x-axis minus the area below the x-axis. In this case, it turns out that the definite integral from 0 to 2 of that function actually equals 0. It's the same area above the x-axis as there is below. Those two areas balance each other out exactly. We often think of this area above the x-axis as positive area and the stuff below as negative area. One thing to notice with the limits of integration that I usually put the lower limit first, so that the smaller of the two, so 0 to 2. That won't always be the case. We'll see some examples where it gets flipped around, but when we read aloud the integral, we always read from bottom to top. I say this as the definite integral from 0 to 2. All right, let's take a look at some more examples. Here's a geometric example. How would I compute the definite integral from 0 to 4 of g of x dx, where g of x is the function graphed here? I think about it in terms of positive areas and negative areas. I have a certain amount of area below the x-axis and a certain amount above. And I only want to go from 0 to 4, so I'm only interested in the part that's to the right of the y-axis. Okay, let's compute these areas. Well, I can kind of block this off into some geometric parts. I see I have an area of 1, and there's an area of 1/2. And then for the semicircle, let's see, the area of a circle is pi r squared, so I only want half of that, 1/2 pi times the radius squared, and the radius is 1. So that's it, 1/2 pi. So the total answer to my problem is 1/2 pi minus, and then the total area below, 3/2. Let's take a look at a couple more examples. How about the integral from 0 to 5 of 4 minus x dx? Well, this is really a geometric example. I'll have to draw it out to get a picture. But I can see that the graph of this, so this is a line with slope -1 that crosses the y-axis at 4. 4. But I want the integral from 0 to 5. So I have a certain amount above the x-axis and a certain amount below the x-axis. So how much do I have above the x-axis? Well, I can use the formula for a triangle, 1/2 base times height. So there's 8 units above the x-axis. And we can see this is half of a unit square, so I end up with 1/2 below. So my answer is 7.5, that's 8 minus 1/2 as my answer, or 15/2. How about the next problem? This one's a little trickier. Can you see what the function looks like if I were to graph it? So that function is actually a semicircle with radius 5. The area for a circle is pi times the radius squared. So for a semicircle, we will want 1/2 pi r squared. I have the 5 squared. So how about 25/2 pi as my answer? There we go. So how do we actually compute the area? How do I actually compute this definite integral when I can't just use simple geometry? And this is really where calculus comes in. If I have a function like x squared, how will I compute area below that graph and above the x-axis? 2 steps. Number 1, find a Riemann sum approximation using n rectangles. then step number 2, take the limit of that sum as n goes to infinity. So let's work this out. The algebra can get a little tricky, but it's not too bad. So let's make a Riemann sum approximation. Using right rectangles, we find every rectangle has width 1 over n. The right endpoint of each rectangle lies at 1 plus k over n. And the function evaluated at the right endpoints looks like 1 plus kn, that quantity squared. So the Riemann sum, the area of the n rectangles, is the summation as k goes from 1 to n of this expression. I'll skip a few steps here, but what happens when we simplify that? It turns out we get an expression that is 7/3 plus 3 over 2n plus 1 over 6n squared. That is the area of the Riemann sum approximation with n rectangles. It's not the full area under the curve yet. That's just a rectangle approximation. But now, here's the step 2. I take the limit as n goes to infinity, as the number of rectangles goes to infinity, and this whole expression turns into 7/3. And that is the true area under the curve. That is the true area there. And it's kind of impressive that we can do that. This is the power of calculus, that we can find the real area. Okay, let me back up a little bit. Now I'm going to take some time showing how this simplification works. I need to simplify this summation. So this equals, I'll expand the binomial there. So the summation k equals 1 to n of 1, and you can just FOIL this out. It looks like we end up with 2k over n plus k squared over n squared, all times 1 over n. And then I can multiply my 1 over n through. I'll distribute the 1 over n. And I end up with summation k equals 1 to n, 1 over n plus 2k over n squared plus k squared over n cubed. Now, summation just means I'm adding a bunch of stuff together. So I'm adding these three terms n times. So I can split this up. I can add the first term n times, and then add the second term n times, and then add the third term. So I can easily write this as the summation k equals 1 to n of 1 over n plus the summation k equals 1 to n of 2k over n squared plus the summation k equals 1 to n of k squared over n cubed. Now look what happens here. N is a constant. N does not change. K is the variable that's changing. So as k changes from 1 to n, what's happening to the summand? It just stays 1 over n plus 1 over n plus 1 over n plus 1 over n. And if I add 1 over n to itself n times, what do I end up with? 1. How about my second summation? Notice what is constant here is the 2 over n squared. It's the k that changes. So I'm adding a bunch of terms with a constant factor of 2 over n squared, which means I can factor out the 2 over n squared, and the rest of the summation remains. K equals 1 to n of simply k. Do you see what the constant is for this third summation? It's the 1 over n cubed. So I can factor out 1 over n cubed, summation k equals 1 to n of k squared. This is where I need to introduce some summation identities, because it turns out that these two summations that are simple and have nice forms have identities for their values. So it turns out that the summation k equals 1 to n of simply k, well, that's 1 plus 2 plus 3 plus all the way up to n, can be simply expressed as n times n plus 1 all over 2. And it also turns out that the summation k equals 1 to n of k squared, that's just 1 squared plus 2 squared plus 3 squared plus all the way up to n squared, that has a formula also, n times n plus 1 times 2n plus 1 all over 6. You don't need to memorize these, and at times that you will need them in problems, I will show them to you, so you'll have those ready when you need them. I can now write, this is 1 plus 2 over n squared times n times n plus 1 over 2 plus 1 over n cubed times n times n plus 1 times 2n plus 1 all over 6. What I've done is I've turned this into what we call closed form. Is that I don't have a summation anymore. Now it really is a formula. I really can plug in a value of n and find the answer. Well, let's do some simplifying. This is 1 plus, let me cancel out the 2's, and I can cancel out a factor of n. So I end up with n plus 1 over n. And then for my last term, I can cancel out one of those factors of n, cancel out an n there. And in the denominator, I'll have 6n squared. In the numerator, let me expand that out. So do some FOIL. You get 2n squared plus 3n plus 1. All right, now we're almost done. Not too much now. So I'll distribute the denominators. So this becomes 1 plus, now I have n over n, which is 1, and 1 over n. And 2n squared over 6n squared looks like 1/3. 3n over 6n squared looks like a 1/2, maybe 1 over 2n. And plus 1 over 6n squared. And let's add together what we can. It looks like some constants are the 1, and the 1/3, so that's 7/3. I also have a 1 over n and a 1 over 2n. I can, this 1 over n, I can call that 2 over 2n. Combine those together, I get 3 over 2n. And lastly, I'm left with the 1 over 6n squared. And that is it. That was the simplification that I needed. That's how the summation simplifies. So let's recall where this took us in the problem. Once I could simplify that summation, that's really what told me the Riemann sum approximation with n, and I could take the limit as n goes to infinity. All right. This brings us to the final slide, which is simply a summary of the ideas. This is really how the definite integral is defined. The definite integral from a to b of a function f of x dx is defined as the limit of Riemann sums. I make a Riemann sum approximation using n rectangles, and then I take the limit as n, the number of rectangles, goes to infinity. That makes this approximation better and better and better and better as the number of rectangles goes to infinity, which ultimately gives us the true area. And so this definite integral is the true area, and we get it from taking a limit of Riemann sum approximations. All right, give the homework problems a try. Don't be scared of getting your hands a little bit messy with some of the algebra. You can do it, and be sure to contact me if you have any questions.